This video is going to cover Pythagorean's theorem and radicals. Which is, a radical is just that symbol right there, and you guys probably call them square roots. It's a square root if it just looks like that, but there's other radicals that we won't get into, that you'll get into in later maths. This goes along with assignment number 8. So we're going to talk about using Pythagorean's theorem to solve for the missing side of a right triangle, the converse of Pythagorean's theorem. Hopefully most of you know that Pythagorean's theorem is a squared plus b squared equals c squared, where a and b are the legs, c is the hypotenuse. All the converse of that says is that if three numbers, whatever those numbers are, if they fit into Pythagorean's theorem, then that triangle has to be a right triangle. And there's some common Pythagorean triples that we're going to talk about, that if you know them, it makes everything go a lot easier and you don't have to do so much math. On your calculators, a couple of things on your calculators. If you're trying to do the square root of something, then you hit the second button. If you have this calculator, you hit the second button, and then you hit the x squared button. You can notice that the radical, the square root's right above it. So if you're trying to do the square root of 92 or something, then you hit you hit second, then that button, then 92, and hit equals, and it'll tell it to you. Same idea on this one, you hit second, and there's your square roots above that button. If you have a Casio calculator and you're doing square roots, it will give you the answer in radical form. In other words, it'll give you some answer that maybe looks like this: 3 times the square root of 5. And for some of the stuff that we're going to do, that's going to be a good thing, because we want some of our answers in radical form for what we're going to do next. But for a lot of them we don't, and what you'll have to do is, if you go in on your Casio, you'll have to go into, I believe it's the mode button on the Casio, and change it so that it gives you a decimal answer instead of that radical answer. If you have questions about that, you could email me and I'll try to tell it to you. But on what we're going to do right now, if that Casio is giving you this radical form, that's going to be a good thing, because you could just punch this stuff into your calculator and it'll simplify down these radicals for you, because that's the first thing we're going to do here. Simplifying radicals. When we're simplifying radicals, what we're doing is we're given exact answers, not some rounded off answer, just like when you have a calculator and we've done stuff like this. And we've talked about when you're dividing something and it comes out to be 5.33 and it keeps repeating, and you have to round it off somewhere. It's like 5.33. Instead of that, we said that you can write that as 5 1/3. That's an exact answer. This would be a rounded off answer. With radicals, that's what we're going to do, is we're going to, sometimes we want those exact answers. All right, now not all the time. On some of the problems, it's going to say round to the nearest tenth or whatever, and so then you just use your calculator and round off the answer. But for these, when I'm simplifying radicals, as I show you this, I want you to give the answer in radical form, which I'm going to show you. So if we're simplifying this, first thing, these are perfect square numbers. All that means is that each one of them, if we took the square root of them, so if I took the square root of 64, it's going to come out exactly 8. It's going to come out even. There is no radical there. We got to know these perfect square numbers, and we got to be able to use them. On this first one, all you're going to do with these first few is, it's like your tree diagrams that you made back when you were in 4th or 5th grade, whatever it was, and you break this apart into 9 times 2, and then you break this apart into 3 times 2, and you write down that the factored form is 3 times 3 times 2. That's sort of what we're doing here. We're going to find one of these perfect square numbers that'll divide evenly into that number that's under that square root symbol. In this case, it's 25. So I'm going to split this apart into the square root of 25 times whatever times 25 gives us 75, which is 3. And then the reason that we do this is because now that square root of 25, we can actually do the square root. Square root of 25 is just 5. So that 5 part comes out of the radical. The 3 stays under the radical. That's our simplified form. This is just read 5 times the square root of 3, or 5 radical 3. That is the exact same thing as this, only simplified. And we could punch in the square root of 75 on our calculator and get the decimal answer, but this is an exact answer, and that answer would be a rounded off answer. So if we want an exact answer, then this is what we leave it, and it's just simplifying the radical. Same thing on this next one. I look for a perfect square that will divide into 18 evenly, and I notice that 9 will. You always want the biggest perfect square too. So 9 times 2, so you got 9 times the square root of 9 times square root of 2. That's exactly the same thing as the square root of 18. Here, square root of 9 is just 3. That comes out from underneath the radical. 2 stays under the radical. That's your simplified form. Next one. The reason I put this one on here, you got to be careful with something like this. You can't just divide and say, okay, 2 will go into 12 6 times. It doesn't work. 2 is a regular number. The 12 is under the radical, so they're 2 different kinds of numbers. You can't divide them or add them or multiply them or anything else, since they're different kinds of terms. So here what we're going to do is we're going to just work with the top there, and we're going to break down that 12 and say that's the square root of 4 times the square root of 3. Square root of 4, remember, we always want one of them to be a perfect number. We could have broke 12 down into the square root of 6 times square root of 2, but neither one of those is a perfect square number, so it doesn't really help us. Square root of 4 here is 2. Square root of 3 just stays the square root of 3, and I still have this 2 on the bottom. Now, once I have this, now we can simplify with these, because these are both regular numbers. So I can say 2 will go into 2 once, 2 will go into 2 once. They sort of cancel each other out there, and you're left with just the square root of 3. That's your final answer. So all of this simplified down into just radical 3 or square root of 3. So there, on these kind, you're looking, and that's one of the things with simplifying. There's many, many different ways to simplify with radicals, and we're going to talk about a couple others. But you're looking for a perfect square number that will divide evenly into the number that's under your radical. Next one, rationalizing. What rationalizing means, and a lot of books have gotten away from this. A lot of books don't care about it anymore. Just like they don't care about reducing fractions. But rationalizing, you're not supposed to leave a radical in the denominator of a fraction. Well, the way that we can undo that is just multiplying the top and the bottom by whatever that bottom radical is. So here we're going to multiply the bottom by the square root of 2, and we're going to multiply the top by the square root of 2. We end up with, and here we can multiply these. Since they're both radicals, we just multiply the numbers. So we end up with square root of 24 over the square root of 2 times 2 is 4. On bottom, the square root of 4 is a perfect square number, is just 2. So now we no longer have a radical in the denominator. On top, we got the square root of 24. Well, we can simplify that like we were doing on the last slide and I'm going to break that down into the square root of 4, because that's a perfect square number, times the square root of 6. 4 times 6 is 24. The square root of 4 is 2. So I got 2 times the square root of 6 on top over 2. Same thing that we said on one on the other slide. These 2's then just cancel out, and you're left with just the square root of 6, and that's your final answer. That's in simplest form. Some of you probably looked at this and said, well, 12 divided by 2 is square root of 6, and you could have just done that. And you're right, you could have, since these are both radicals, we could just divide them, and here we end up with just the square root of 9. Well, the square root of 9 is 3, so all of that simplifies down into just regular 3. Next one, to rationalize this one, 3 won't go into 14 evenly, so that's not going to work. So what we're going to do is we're going to multiply the top by the square root of 3, multiply the bottom by the square root of 3. On top, you end up with the square root of 42. On bottom, you end up with the square root of 9. On bottom, the square root of 9 is just 3. That comes out from underneath the radical. On top, square root of 42. If we look up through here and try to figure out a perfect square number that'll divide evenly into 42, 4 won't, 9 won't, 16 won't, 25 won't, 36 won't, 49's too big, and everything else is going to be too big. So the square root of 42 won't simplify any. So our final answer is just square root of 42 divided by 3. That's in simplest form. Again, a lot of books now are just, if they had this, they would just leave it that way and not rationalize it. If you're multiplying with radicals, all you're going to do, if you have 2 radicals here, is multiply them together. Now you got to be careful when you're multiplying like an x times a y, that gives you xy. But when you add x plus y, you can't really do anything with that. It just leaves you with x plus y. So with addition and subtraction, it's a little different than with multiplication and division. Here we can multiply these, so we get square root of 5 times 20 is 100. Square root of 100 is just 10. So all of that simplified down into just regular 10. Next one, this one, 6 times 3 is going to be 18. So now we got the square root of 18. Well, we can simplify that by breaking it apart. Square root of 9 times the square root of 2. Square root of 9 is 3. That comes out of the radical. Don't put the square root back around it. And that's times square root of 2. You can't do anything with that, so it's 3 times the square root of 2. This is, treat these radicals just like they're variables. So this is like saying 3x is what we're saying there, except we're saying 3 square root of 2. 3 times the square root of 2. This is 3 is your coefficient, and this is like your variable. Again, this is an exact answer. If we plugged it into our calculator, we get a rounded off answer, and sometimes we want to be exact. If we have something like this and we're just multiplying, you multiply the regular numbers and you multiply the numbers under the radical. So 3 times 4 is 12. That's still outside. And then inside, 5 times 15 is 75. So it's 12 times the square root of 75. Well, 75 will simplify down. So I'm going to break it down into 25 and 3. So we got 12 times the square root of 25 times the square root of 3. Well, the square root of 25 is just 5, so this is 12 times 5 times the square root of 3. And these numbers that are outside here, we can go ahead and multiply them together. 12 times 5, ignore that. 12, I'm going to write it up here. 12 times 5 is 60. And then we still got times the square root of 3. So 60 times the square root of 3 is our simplified answer. All of this simplifies down into just 60 times radical 3, or square root of 3. if we're adding, same idea as with variables, if you're adding with variables, so if we have something like 2x plus 5x, that gives us 7x. But if we have 2x plus 5y, we can't add those together because they're not like terms, so that's in simplest form. So if we were looking at this one, we can't really add these right now the way that they are, but the square root of 20 will simplify down. It'll break down in square root of 4 times the square root of 5. Well, the square root of 4 is 2, and the 5 stays the same underneath there. So now what we have is both of these have the square root of 5. So to add them or to subtract them, we're just going to combine the coefficients out in front. So it's 5 plus 2 is 7, and then the number underneath the radical just stays the same. So 7 radical 5. All of this simplifies down into just 7 times the square root of 5. Treat them like they're variables, like they're x's. Next one. On this one, if you had 7x and plus 1x, and this, all this works for subtraction too. I just only put addition on here. 7x plus 1x, that would be 8x. Same idea here. You got to remember that that coefficient in front of the x, if there's not 1, is a 1. So on this, it's going to be 7 plus 1, that's 8. And then the square root of 3 just stays the same. So that simplifies to just 8 times the square root of 3. Next one, we look at these three terms, and we should notice that this one and this one are like terms because they both have that square root of 5. So we're going to put those together. That gives us 9 times the square root of 5 plus here the 4 times square root of 15. If I tried to break square root of 15 down, there's no perfect square number that'll divide evenly into it, so it won't simplify any. So it's just 4 times the square root of 15. That's in simplest form. That's sort of like trying to put x's and y's together. You can't do anything to it. That's just in the simplest form. All right, Pythagorean's theorem. Pythagorean's theorem, first thing you got to know about Pythagorean's theorem, it only works for right triangles. It's got to be a right triangle, so the triangle has to have a right angle in it. A squared plus b squared equals c squared. Most of you have dealt with Pythagorean's theorem at some point, so hopefully you remember this has to be a leg, and the b has to be one of your legs. The c is your hypotenuse. The hypotenuse in a right triangle is always the longest side, and it's always across from the right angle. That's the first thing you should do every time that you see a right triangle, whatever it looks like. Find your hypotenuse. It's always across from the right angle. That's got to be the C part. Then these other parts are your legs, and it doesn't matter which one is A and which one is B. It makes no difference. So A and B are legs, C is the hypotenuse. Most of you have dealt with Pythagorean's theorem. The bad thing is that when you dealt with Pythagorean's theorem, a lot of you just dealt with, they tell you this leg was 5, this leg was 7, and they want you to find the hypotenuse. And that's the way it was set up every time, is where they told you the 2 legs, and you were just finding the hypotenuse. Well, sometimes you're going to want to find a leg, whichever one it is, with the stuff that we do, so you got to know how to work the formula and work it backwards some of the times. On your worksheet, I'm going to do a few examples here, and then we'll go back to the notes a little bit. If I'm looking at this worksheet, just picking out something like number 5, this is dealing with the radicals. It's got the square root of 175. I just got to find a perfect square number that'll divide evenly into that. Stuff like 175, 200, 275, all those numbers. If you're dealing with money, you should know that quarters will go evenly into it. So 25 will go into it. Now that might not be the biggest one, but It'll help us to get it simplified down, just like with fractions. When you're reducing a fraction, you usually want to divide by the biggest number, because then you can take it down quicker. But if not, you can always divide it again. So 25, if I got $1.75, that means I got 7 quarters. So 7 times 25 is 175. Square root of 25 is 5. That comes out of the radical. 7 stays under the radical. That's your simplest answer. That's simple form. We'll do number 11 just to show you another one. You got radical 5 times 2 times 4 times the square root of 8. Since this is times, we're going to times the coefficients together, so that's going to give us 20, and we're going to times the radicals together, so that's going to give us 16. If it was addition, then we'd have to try something else. So here we got 20, the square root of 16, that is a perfect square number, and that's just 4, so that comes out of the radical. You end up with just 20 times 4, which is 80. So all of that simplifies down to just the regular number 80. All right, we're going to do a couple of the Pythagorean theorem problems. We'll do like number 16. On these, it says round your answer to the nearest tenth. So these, we're not going to try to simplify radicals or anything. We're just going to take our calculator and let the calculator do the work and round our answer off to 1 decimal place. So here we got 3, 10, and x. This is a leg, 3 is a leg, 10's a leg, and the x is the hypotenuse. So when I go to plug into a squared plus b squared equals c squared, I know where each thing goes. The 3 can go in here for a, so we're going to do 3 squared plus 10 squared equals, we don't know x, so that's just x squared. And then we just do a little bit of math, 3 squared. And you could punch all this right into your calculator, and it's going to give you that answer for all of that. 3 squared is 9, 10 squared is 100, 9 plus 100 is 109, and we got x squared on the other side. Now all you're going to do once you get to this point is you take the square root of both sides. The square root of x squared is just x, and the square root of 109, you grab your calculator and you figure out what the square root of 109 is. On your calculator, remember most of your calculators you'll have to hit second, then find that square root, punch in 109, and I come up with 10.4403 something. It said round it off to the nearest tenth, so that'd be 1 decimal place. So our answer is going to be about 10.4. So we're not coming up with an exact answer here. If we were coming up with an exact answer, then we would look at square root of 109 and try to simplify it down, which it won't simplify. And we could just leave our answer that way. This would be an exact answer. This is the rounded off answer. Next one, if I look at number 20, let's do 24. They tell us that's a right angle, so right away I know that that side over there is my hypotenuse. This is x, this is 6.5, that's the hypotenuse. And this side over here is 2.7. Got to make sure that you set these up right. Again, most of you are used to every single problem being like this, where the hypotenuse is the variable. That's not the case this time. So here, our A, we're going to let that be 2.7. That's one of the legs. This is the other leg. So it's 2.7 squared plus x squared equals 6.5 squared. If you do all this in your calculator, you could just move this 2.7 over to the other side, subtract it off, and it would work out. I'm going to go ahead and just work it out here, and then I'll go back and maybe try to show you how to do it so that you don't have to keep punching in stuff in your calculator all the time. So we get 2.7, we square it, not square root, but square it. Comes out 7.29 plus x squared equals, we do 6.5 squared, comes out 42.25. Then what we're going to do is subtract 7.29 on both sides. These cancel out. You're left with x squared on the left minus 7.29. And that gives me 34.96. So these have an extra step. When you're looking for one of the legs, has an extra step than the ones that dealt with just finding the hypotenuse. Next thing we got to do is we got to take the square root of both sides. Over here, the square root and the 2 are going to cancel out, and that leaves you with just x. And then you grab your calculator and you hit second square root, 34.96. And it said round it off to the nearest tenth, and I come up with about 5.9. The last thing I would do on a problem like this one is go up here and make sure that 5.9 makes sense. We know that that 5.9 was supposed to be a leg, so it should be smaller than that hypotenuse, and it is. So that seems like it should make sense. So hopefully Pythagorean's theorem, hopefully you can do most of those. We'll probably come back to the worksheet here in a minute, but I want to talk about, actually, let's see here. Let's jump on. Let's go ahead, we'll do one more. We'll do number 25. 25 looks like this. It's got 8 there, 15 there, x there. That's your hypotenuse. So we're looking for the hypotenuse this time. So these two are going to be your two legs. So 8 squared plus 15 squared should equal x squared. 8 squared is 64, 15 squared is 225, x squared. Add those together and we get 289 equals x squared. Take the square root of both sides. The square root and the 2 over here cancel out, leave you with just x. The square root of 289, you grab your calculator and you do the square root of 289. Second square root 289. And what do you know, it comes out even. So the length of that hypotenuse right there has to be 17. And this leads me into what I want to talk about next, and that's the fact that sometimes you have special sets of numbers that are always going to work for Pythagorean's theorem, and one of those special sets is one leg is 8, one leg is 15, then the hypotenuse is always 17. So if you see a triangle, instead of having to do all this work all the time, you see a triangle where it has a leg that's 8, and maybe the hypotenuse is 17, you can use this triple right here, it's called a Pythagorean triple, and know that this other leg here has to be 15, instead of doing all the math or all the work for it. So if I see a problem that looked like this one, and I knew that one leg was 8 and the other leg was 15, and I was looking for that hypotenuse, I know right off the bat that hypotenuse has to be 17 because of this Pythagorean triple. A lot of times I call them families. And these are 4 of the families, or 4 of the Pythagorean triples that get used a lot. And these ones that I have listed here are like the head of the family. And then there's other things that fit underneath it. And the way we get those others is just by multiplying or dividing. And a lot of times this will make everything a whole lot easier if you know these. So one Pythagorean triple, and the one that probably gets used the most, is 3, 4, 5. So if you have a triangle, a right triangle, and we know one of the legs is 3, one of the legs is 4, the hypotenuse has to be 5. If we plug that into Pythagorean's theorem, 3 squared plus 4 squared equals 5 squared, it's going to come out to work. Now what you can do with this to find other ones, because they're not always just going to use 3, 4, and 5. If we doubled each one of those, so if we multiplied each number by 2, we'd get 6, 8, and 10. That's another member of this family. So if you see a triangle, and it's got a leg that's 8, and the hypotenuse is 10, you can figure out this other leg has to be 6. If all this confuses you about these Pythagorean triples or the families, then use Pythagorean's theorem and it's going to work out the same every time. We could triple each one of them, 9, 12, 15. We could multiply each one by 10, get 30, 40, and then that means the hypotenuse would have to be 50. Remember, the hypotenuse always has to be the longest one of the 3. We could multiply them all by 100 and get 300, 400, and then the hypotenuse would have to be 500. But those are all different kinds of Pythagorean triples that fit into this 3, 4, 5 family. And there's many, 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 many more, right? Not just the ones I have listed here. You could also have something like this one. Let's get rid of that. 3/5, 4/5. Well, guess what this one's going to have to be? If this is 3, this is 4, that's got to be 5/5, which would be just 1. So if we had a right triangle, and one of the legs was 3/5, and another leg was 4/5, that hypotenuse over there has to be 5/5, or just 1. And I didn't have to do all the math and try to use Pythagorean's theorem and squaring these fractions and everything else. Another Pythagorean triple is 5, 12, 13. Some other ones that would fit in that family if we doubled it, 10, 24, 26. If we tripled it, that'd be 15, 36, 39. If we times it by 10, 50, 60, not 60, 120. Sorry, I was times it by 5. And 130. So if you're given a triangle, and you know this leg is 50, this leg's 120, instead of setting up Pythagorean's theorem and doing 50 squared plus 120 squared equals x squared and solving it out, if you can remember that it fits into that Pythagorean triple, then we can find this hypotenuse just because it's got to be 5, 12, 13. It's got to fit into that. If I multiply the 5 by 10, I multiply the 12 by 10, then I got to multiply this 13 by 10, and I get 130 there. Same idea on this one. 8, 15, 17 is another Pythagorean triple. If we doubled it, 16, 30, 34. If we times it by 10, 80, 150, 170. Those are all Pythagorean triples, and just if you can remember them, and we just got done doing that one problem, if you can remember them, then it'll cut down on some of your work. And the last one here, 7, 24, 25. If we doubled it, it'd be 14, 48, 50. It's another one that fits in that family. If we multiplied by 10, 70, 240, and 250. If we multiplied by 100, be 700, 2400, 2500. So if I had a triangle, and I knew the hypotenuse was 2500, and I knew that this leg over here was 2400, and I was looking for that leg, it has to be 700. And we could do Pythagorean's theorem and solve it that way, but if you can see that it fits into one of these triples, sometimes it'll make it easier. Next thing, if three sides of a triangle fit into Pythagorean's theorem, then the triangle is a right triangle. So if I have some triangle, and I don't know that it's got a right angle in it, and I want to see if this is a right angle or not, and maybe this side's 7, this side's 6, and this side is 12, then all I do is put it into Pythagorean's theorem. Remember, the longest side has to be the hypotenuse. So I do 7 squared plus 6 squared equals 12 squared, and see if it comes out right or not. 7 squared is 49, 6 squared is 36, 12 squared is 144. If I add 49 and 36, I get 85. And we're saying 85 equals 144. Well, 85 doesn't equal 144. So we know that this is not a right triangle. It's not a right triangle because it didn't fit into Pythagorean's theorem. 7, 5, and 9, if we tried that, we do 7 squared plus 5 squared equals 9 squared. 9 squared is 81. 7 squared is 49. 5 squared is 25. 49 plus 25 is 74. 74 doesn't equal 81, so these sides do not make a right triangle. 15, 25, and 20, you got to be careful here. Remember that the hypotenuse has to be the longest side, so that's the 25. So if we look at that, we would do 15 squared plus 20 squared equals 25 squared. And I wouldn't even do the math here because I would look at this and I realize that that fits into that 3, 4, 5 family or Pythagorean triple. 3 times 5 gives you 15. 4 times 5 gives you 20. Well, then that means this side has to be 5 times 5, which is 25. So that tells me, yes, this one is a right triangle. Same idea on this one. If you notice with the radicals here, they're trying to make it hard on you. But if you just did Pythagorean's theorem, if it was 3 squared plus 4 squared, or radical 4 squared, sorry, equals the square root of 5 squared. All that's going to happen here is that radical and that 2 are going to cancel out and leave you with 3. This radical and this 2 are going to cancel out and leave you with 4. And this radical and this 2 is going to cancel out and leave you with 5. 3 plus 4 is 7. 7 doesn't equal 5. So this one is a no. And you got to be careful on this one because if you look at it and you think, all right, I got a 3 here, I got a 4 here, and I got a 5 here. That's true, but it doesn't fit that 3, 4, 5 family because just taking the square root, that's something a little different. You're not just multiplying it by 2 or multiplying it by 10 or dividing it by 2 or whatever. It's something a little different when you're taking the radical. So that one is a no. All right, so your assignment's that worksheet. Probably what I'll do is later on in the week I'll just send out the answers and let you try to check it.